Thanks, Beth. Hello, everyone. Welcome to today's webinar on calculating energy costs. All of PGE's trainings are in part sponsored by Energy Trust of Oregon. We work together to make sure the concepts and recommendations you learn are consistent across all of our individual programs and services. For today's webinar, we assume you are a non-technical business professional with an interest in learning about managing electricity with the goal of saving energy. The examples used today will be typical energy-intensive systems, non-residential places of work such as office buildings, campus, retail stores, governmental office buildings, and industrial processing plants. Today we have a simplified agenda. In measuring electricity, we will review the basic formulas needed to measure electricity usage at your place of business. In calculating energy savings for efficiency projects, in calculating energy savings for efficiency projects, we will expand the formulas to include the price of electricity so we can calculate the cost of electricity usage for common business equipment. With these basic formulas, we can perform a project evaluation for improvement projects that can save energy and money for your organization. Lastly, we'll provide contacts for getting advice and help with projects to make sure you are getting all the incentives and support to get your projects approved and completed. It has been a basic tenet of good business training that managing anything starts with a focus on measurement. Measurement is the first step in good energy management. Measurement begins at the decision point of purchase of new or replacement equipment and continues throughout the normal operations of your business unit. A place to start with measurement are the labels on the box or nameplates on the equipment, which are required by federal code and must include information about the electrical requirements of the equipment. For electricity, the universal measurement that will be found on these labels are watts, volts, amps, which we will discuss in the following slides. Once you have purchased the equipment, these key measurements of electricity are locked in and are difficult to change without expensive replacement or retrofit. Many of you here today may have been exposed to energy or management training programs. The PDCA, or Plan, Do, Check, Act cycle, pictured here, is a common theme in these programs. Measurement is critical in the planning stage and the checking stage. If your initial measurements in the planning stage are accurate, as proved in the check stage, you will build credibility for getting your future projects approved. Measurement is critical to gaining approval to make changes to purchase decisions or changes to existing operations. All organizations have a management cycle where budgets are established to fund the most deserving projects for the coming years. Without good measurement, projects won't likely get approvals and funds. So what do all these terms mean? The volt, the amp, and the watt. These terms are part of any training program for professional energy experts and come from Ohm's law, which is a much more complex and complete measurement of electrical energy fundamentals. Sometimes you may be in a room with experts and their terms will be slightly different. For example, volts may be shown as the letter E instead of a V. Amps may be shown as the letter I instead of an A. Watts may be shown as the letter P instead of a W. The simple math formulas we learned today are the same regardless of what letters are used. So here's a simple visualization. Electricity is a very powerful and useful energy source, but it doesn't have a physical form as most other resources we use, such as natural gas, gasoline, diesel fuel, coal, and water. So it is common to explain electricity with analogies and visual aids. In this example, volt is shown as the driving force behind the amps, as it tries to overcome the ohm's efforts to provide resistance. The most common analogy for electricity is to visualize elements of a water system. The water pressure in your home or place of business is similar to the voltage pressure. A low water pressure problem is the same as a low voltage problem. in that your equipment doesn't work well. The volume of water flowing through the pipe is similar to the amounts of amps flowing through the wire. The total water delivered is a function of both pressure and flow. Think of a fire truck that adds water pressure and increases the size of the hose to deliver more total water than your low pressure and smaller size garden hose. The total electric power is a function of volts and amps. Think of the difference between a major power plant that generates at thousands of volts and thousands of amps compared to your home that uses electricity at 120 volts and about 15 amps at that wall socket. The size of the pipe provides more or less resistance to the flow of water, and the size of the wire provides more or less resistance to the flow of amps. So let's review the basic definitions. I'm having a technical issue advancing these. So volt is the amount of force or potential applied. Amp is the amount of electrons flowing. The watt is the volts times the amps times something called the power factor. For single-phase equipment, residential and most commercial lighting and plug-ins is single-phase. If you have a larger commercial or industrial operation, you will take that formula times the square root of 3 for larger commercial and industrial equipment and operations. These are the basic math formulas. Ohms, the amount of resistance to the flow, will not be used in today's calculations.
John, I have a question. Which of these terms will a customer actually see on their bill?
That's a great question, Beth. I think the next slides will help answer that question. So energy demand is something you might find on your bill. It involves the rate of use, measured as kW. There's energy use, the total energy used, measured as kWh, and this accounts for most of the costs on an energy bill. Reactive demand may show up as kVAR charges on a bill for larger commercial and industrial customers. Demand response is an emerging offer to customers from their utility involving the smart grid and its applications. Dispatchable standby generation is where a utility puts backup generators that you have online to use when the region has a critical need for power. Large hospitals, large industrial plants that have backup generators might be interested in this. Time of use is a way to avoid the demand charges mentioned above. The rate of kilowatt hours may change from time to time throughout the day or on weekends. You can take advantage by shifting load from one period to another. On-peak versus off-peak. You may be receiving pricing options that allow you to shift your demand and save money. So let's focus on that kWh that accounts for a large part of your energy bill. Quite often, these terms like kWh mean one thing, but this one means 3. If you say the Trailblazers are part of the NBA, National Basketball Association, that would be one organization. Or the Timbers belong to MLS, which is one organization, Major League Soccer. But kWh has 3 parts that are laminated together. The first part is the magnitude. We go back to the metric system we learned in high school. K is 1,000, M is 1,000,000, G is 10 to the 9th, 9 zeros. So it tells us how many of the units are we going to use in the formula. The middle part is the unit of measure. W, in this case, kWh, stands for watts, but it could be kV for kilovolts, and it could be kVA for kiloamps. The last part is the unit of time. For example, you may see the H in kWh, meaning hours, the amount of kilowatts per hour you're using. It could be an A, which stands for the amount of energy for a year, and sometimes you'll see it as a Y, but most often you'll see it as the letter H. So let's look at a quick example. In this example, we have a group of light bulbs. We look on the label and find the watts, in this case 100 watts each. We have 20 light bulbs for a total of 2,000 kW. To get from watts to kW, we have to divide by 1,000. That would give us a 2,000 divided by 1,000, or 2 kW. Finally, we look at how many hours of use for this particular day, and we say that they are on 8 hours for that day. So 2 times 8 is 16 kWh. This is the simplest way to understand what kWh is about. Find the W, divide by 1,000, and times the hours. So watts divided by 1,000 times the hours gives us kWh. We have just seen an example of the most common used formula for calculating energy use in terms of kWh. Sometimes you may need to know volts and amps and power factor in order to calculate watts. But most often you will find that watts are given to you from the labels on the equipment, or by the energy bill or the energy management software system if you have one. Labels on the packing box or on the equipment are required by federal code and must include information about the electrical requirements of the equipment. So let's use those tools that Beth mentioned at the beginning of this webinar to make your mark on the correct answer to the question on this slide. How many kilowatt hours are used by a 60-watt light bulb that is on 10 hours a day for the next 30 days? So this is a pretty typical example of trying to calculate the kilowatt hour usage for a month for a particular piece of equipment. While you're doing that, I'll tell you a little story. One bulb doesn't use a lot of electricity, but one customer I spoke with was the manager of an auto dealership. The businessman counted the number of bulbs that lit up the sales area, both inside and outside the sales lot. About 1,000 incandescent bulbs was the final count. The monthly bill for this was about $1,000 a month. So a little bulb can add up to be a lot of costs when you have a lot of them. So let's look at the answers. It looks like everyone thinks 18. Let me show you my math. And yes, 60 divided by 1,000 times 300 is 18. Correct answers all. So let's change the bulb and make it it's compact fluorescent in this case, and do the calculation again. Now, which answer do you think is correct? Another customer story I have is from a manager of a multifamily apartment complex. Although each of the almost 100 units are individually metered with their own electric bills, the landlord electric bills included the hallways, the pathways, the parkways, and common areas like the laundry room, and all on the landlord's electric bill. After taking inventory, there were over 600 light bulbs. The potential savings were significant. So let's look at my math on this question, and the answer is 18 divided by 1,000 times the 300, 5.4 kilowatt hours. That's a 70% reduction from the 60-watt bulb. So let's do one more little quiz. This is like the game Jeopardy! Use the chat feature in this case to send a note to Beth when you know the movie and the question asked by one of the main characters. So like Jeopardy! The answer is 1,210,000,000 watts is the answer. What is the question, and more specifically, what is the movie in which this question was asked? I'll give you a little hint. There's my first hint. It is an electric vehicle. My second hint is this particular piece of equipment in that vehicle. And finally, the question is, where am I going to get 1.21 gigawatts as asked by Doc Brown in the movie Back to the Future? Now, when...
Looks like we got one person that got it right before you said it.
Very good. I'm very impressed. I was in the movie hall when this movie was on, and I was elbowing my wife going, ooh, ooh. And the reason, she said, be quiet, but the reason I elbowed her was this is actually real math. Of course, the movie has a lightning bolt striking, and that's what powers this vehicle. And it is in the category of 1.21 gigawatts. So there was some real math in the movie. Now, given the formula we just had, though, you should be able to answer the question, how much does this energy usage, kilowatt hours, does this vehicle take in charging? We know it only used 1 second to charge it. So how many kilowatt hours does it take to charge this electric vehicle in 1 second? Our math, our formula should work. Sure enough, if I take 1,210,000,000 watts, divide by 1,000, in this case 1 second is 1/3600th of an hour, it takes 336 kilowatt hours per charge per trip in this vehicle. If your cost of electricity were 10 cents a kilowatt hour, that's about $33.60 per trip. I would say that's pretty economical for the amount of time traveled. So let's look at some other terms that you might run into at your place of business. You may hear discussions about tons of air conditioning or tons of refrigeration. These are a couple of terms that are very important in commercial and industrial buildings. There will be an efficiency rating on the label. There are several different but similar terms for this rating. The two most common are Energy Efficiency Rating, the EER, or the SEER, Seasonal Energy Efficiency Rating. There are other ratings, but the most important thing to remember is that the higher the efficiency, the less energy it takes to get the job done, and the lower your energy bill will be. In this case, we have two 5-ton air conditioners. They produce exactly the same amount of cold for your operations. But when you use this formula with the efficiency rating, you'll find that one uses 6,000 watts, the other one uses 4,286 watts because it's a higher efficiency, 14 EER. So in purchasing this equipment, you lock in this efficiency rating, these watts, for the next 15 years. Why is that important? Because the 6,000 unit compared to the 4,286 unit is 40% more energy every month that you're using the air conditioning. That's a big difference and a big savings. You might be willing to spend a little more money for that more efficient unit when you can get this kind of a change in your energy bill. Another term you will run into is horsepower. In this case, the efficiency rating is a percent. This compares two 5-horsepower motors, one at 88% efficiency and one at 92% efficiency. And again, you get a very big difference in watts. In this case, 5% more energy is used by the first motor at 4,239 watts compared to the second motor with a higher efficiency. Efficiency makes a difference. Again, motors last 15 years. You're locking in higher energy bills.
John, I had a quick question from a participant. Is EER, Energy Efficiency Rating, the same as COP?
It is not. You would want to talk to an energy engineer, Energy Trust, or Portland General Electric, and they can walk you through these other terms. It is an efficiency term, but it's not normally used on the labels.
And I'm sorry, John, to interrupt you. I have one more question, a different question. What if the motor is on a VFD?
Again, I would say talk to an energy efficiency expert. It turns out that variable speed or variable frequency drives have different characteristics than fixed frequencies. So you need an engineer to understand the load in order to understand how the efficiency works. Wire size is another interesting term. Even though the watts are the same, here's an example of two motors. Both are 48,000 watts. However, one motor is a 480 volt system and the other motor is a 240 volt system. What that means is for the 100 amp or 200 amp circuit is required for these two different motors. On the 240 volt system, the cost of the wire will be higher because it's larger wire for larger amps. The main panel where the circuit comes out of has a limit, an amp rating. If you add 200 amps to that panel, you might exceed it or have a better chance of exceeding the panel and have to replace the whole panel than if you were only adding 100 amps. The bigger the amps leads to bigger wire, which leads to bigger installation costs, is the message. So wire size and the distance from the panel to the equipment is another area where you need to be attentive to make sure you're not locking in higher costs over time. So let's do a quick summary. Calculating energy cost means do the math. This is kind of a pull this out, print it, put it on a bulletin board. Some people like the algebra and some people like the step-by-step procedure. So step-by-step, find the W, then the K, then the H, times the price, and you will come up with what it costs for that particular piece of energy. Or watts divided by 1,000 times hours times the price. So let's do some more math. What are the power costs for lighting this office area each month? The office area has 40 T8 fluorescent ceiling fixtures. Each 3-lamp fixture uses 90 watts. Well, light is on 10 hours a day, 7 days a week. We'll use 8 cents per kilowatt hour as the price of electricity for this example, and we'll assume a 30-day month. You should be able to use the formulas and determine what does it cost per month to light this room. While you're doing that, another story I have is an energy manager is quite often like a crime scene investigator, such as the CSI Las Vegas TV shows, piecing together enough facts and evidence to figure out what is going on. Our energy experts at PGE and the Energy Trust are often CSI experts for our customers, so please feel free to ask for their help. A lot of these look like word problems in school, having to piece together the right elements in the right formula to come up with the answer. Looks like we have some math going on. Let's see how I did this math. So watts divided by 1,000 times the hours times the price. We have 40 fixture at 90 watts. Coming up, divide by 1,000 times 300 hours times 8 cents, $86.40. I talked to one manager in a seminar years ago who did the kinds of calculations we just did and put that as a little note right next to the light switch or the switch for the equipment so that people would know that's what it costs every time you flip the switch. There is a cost to running the equipment, and it isn't free. So let's look at another piece of equipment. I'll lead you through this one. It's a choice between two air conditioners, one at 1,200 watts and one at 1,000 watts. But of course, the more efficient unit costs $100 more. A very common way to evaluate projects is to ask what is the payback period. The budget manager quite often will have rules of thumb on whether or not a project is likely to get funded. We're going to assume the air conditioner is on 6 hours a day for 4 months, assume a 30-day month, and we're looking for what the annual costs are in a year. And let's assume 10 cents a kilowatt hour to keep the math simple. How long will it take to pay back the extra $100 that you're asking for? So let's find the W, 1,200 watts minus 1,000 watts. I will save 200 watts on buying the more efficient equipment. I divide by 1,000, so I know I'm going to save 0.2 kW. The operations hours are 4 months at 30 days at 6 hours, 720 hours a year. If I take 0.2 kW times the 720 hours times the 10 cents, I save $14.40 per year, and can now answer the question of the budget manager, how long does it take to get my money back? $100 divided by $14.40 a year, it will take almost 7 years to get your money back. One of the things you can look for is incentives. If you get a $50 rebate, let's look at what it changes on the payback period. Payback period is now $100 minus the 50 divided by 1440. I just changed the payback period to 3.5 years. The most common rule of thumb I've come across in business is about 3 years. If you're a well-established firm and can look longer term, it may be 5 years. If you're a restaurant or a business with a little more risk, it may be 2 years or even 1 year. So this project with a rebate starts to look better and better and might be considered for funding. So here's another good purchasing manager perspective. A CFL bulb has a 13-watt rating, while LED bulbs have 9. Both produce the same amount of lumens, which is the amount of light, but the LED bulb costs twice as much but lasts a lot longer. So your question I pose to you is buy CFL bulb at $2, 8,000 hours of life, or buy LED bulbs at $5 with a 24,000 hour life. The lights are on 12 hours a day, every day for the whole year. Energy costs are 10 cents, and you are asked to buy 100 bulbs. Which order are you going to place? The CFL or the LED? So use your arrow or your marker and pick one of these. The feedback from one manager who attended last seminar was that many purchases are emergency basis for critical systems. It's done in the evenings or on weekends, and it was common to quickly purchase the cheapest and quickest solution, often without considering the energy use, which locks in the higher bills for the next decade. So he put a label on each piece of equipment that clearly states the efficiency requirements of the replacement equipment. Even if the equipment failed and was replaced on a weekend, the staff had the important purchase information needed without having the purchase department's manuals and standards. I thought that was a really good example. All right, I see people have made their choices. They would buy the LEDs. I'm very impressed because I would too. Let's look at some of the math. So 13 watts at 100 bulbs versus 9 watts at 100 bulbs is about 400, not about, it is 400 watts of savings is my savings. I divide by 1,000 to get 0.4 kW. The hours of operation are 360 hours per month. The energy bill savings for 1 month are about $14.40. I've added $5 at 100 bulbs versus $2 at 100 bulbs. I have $300 added purchase price. The payback for the extra $300 is $14.40 a month, or about 1.75 years. This will pass most tests for budgeting purposes. Beth, I wanted to ask you a question. You've talked to a lot of the energy experts. What are some of the other benefits that they have come up with for changing out lighting?
Yeah, John. Specifically for LED bulbs, additional benefits would be labor savings. You replace bulbs a lot less frequently. There is less heat produced, which results in lower AC costs. And most LED bulbs are dimmable. They're okay for switching on and off, so the startup time isn't slow like some other bulbs would be. Most work well in cold temperature conditions. And there's no mercury, compared to CFL, so you don't have the same needs for recycling. And that's it. Thanks.
Those are all good things to know and add to your request for budget money. Sometimes if you're right at the cutoff line on payback period, one or more of these other elements that Beth mentioned from the experts can change a no to a yes. So keep track of those other benefits. So let's look at a little more advanced way at this project. Let's say the payback period didn't quite do it for getting your project funded. Let's look at what's called a life cycle look. In this example, we have 13-watt bulbs that last 8,000 hours and 9-watt bulbs that last 24,000 hours. What that means is you'll need to purchase the 13-watt bulbs 3 times while only once for the 9-watt bulbs. So we're really looking at what is the cost of 24,000 hours of light, not just 9 versus 13. So the cost of the 24,000 hours of light, 13-watt bulbs will cost you $2 at 13 watts times 100 bulbs times 3 purchase cycles. So that's going to cost you $600. The 13-watt bulb, 100 of those divided by 1,000 times the hours times the price gets you $3,120 over the life of that bulb, of the 3 purchases of that bulb. The 9-watt bulb, the purchases cost you $500 because you only have to buy them once. And for 24,000 hours of light, you only pay $2,160. So now you can see over the life cycle, you have 13-watt bulbs cost you $600. You had to purchase 3 times, $200. They cost you energy bills $3,120 for a total of $3,720. If you buy the LED 9-watt bulbs, you only have to buy them once for 24,000 hours of light. Plus the energy bill, $2,160, you only pay $2,660. The 9-watt LEDs will be 28.5% cheaper over the life of the product compared to the other bulbs. So that's a life cycle look, and quite often, again, that can change a maybe into a definite yes when you do life cycle analysis. So let's look at what I like to say is the future of energy, the shape. If you did a lot of numbers and showed someone a spreadsheet of monthly bills over a 3 or 4 year period, and you run into your boss and go, look, and the answer might be, oh my gosh, the numbers are overwhelming, they don't like math, spreadsheets aren't fun to look at. I advise you to convert things to a graph. Graphs communicate to people whether they're science or liberal arts or math or not. You can see the difference and communicate to a wide variety of people about what's going on. In this example, this is 4 years worth of data on a monthly basis. I've run it and put January and December in the middle because this is heating equipment. It's a heat pump system. And I put the winter right in the middle of the graph, so it's a year with the winter in the middle. And 2 years have very high winter bills, and 2 years have low bills. And of course, the reason it went from high to low is in the middle, we got a replacement, a much more efficient heat pump. And it made about a 40% difference in the monthly winter bills. You can see that here very easily by looking at the chart. Here's the bill before I made the change, and here's the bills after I made the change. Much easier, especially in communicating that to my wife, than looking at a spreadsheet and going, look at the numbers this way. So I advise you that you can quickly change information from numbers to graphs and have a very good effect. Another way you can do this is to show the 2 years, make the change, and then you track and see whether or not the bills were actually lower. So a very good tracking mechanism. So let's look at a more commercial building. In this case, this is a school building who has an energy management system on it and can analyze data at an hourly and even maybe 15-minute intervals. And when you first look at this chart, as I did, I was a little overwhelmed, but it is 30 days in a month, and each day is plotted. And of course, on the left and the right-hand side, you have midnight, and right in the middle is 12 o'clock noon. So here's noontime right there. When it was explained to me then that this takes shapes, you can see that up here we have the Monday through Fridays, and that makes perfect sense that by 8 o'clock all the students have arrived and you're using a lot of energy. And then it starts tapering off until finally you're down to midnight again. Here we have Sundays, and here we have the Saturdays in the month. So that helped me a lot to understand the shape. And now, without looking at any data or having any knowledge of kilowatt hours or anything else, I can ask some really intelligent questions. And this is an exact example of what a manager did at the school. And he asked the staff, looked over here and saw that every night at about 1 a.m., something came on and stayed on every night. No one had the answer. What was going on? What jumps on and stays on 30 days every month? Finally, someone in the IT department said, that might be us. They purchased some software that turns on all the computers, backs them up throughout the night. The manager asked the IT department, well, how long does that actually take? And the answer was about an hour. But the software isn't smart enough to turn the computers back off, and so they stay on for this period of time in this area. If I can draw this. So it comes on and stays on. The manager said, well, what would it cost if I wanted it to turn it off? I could save all this energy in this block. And they worked out a deal to buy a little more expensive software that would turn the computers off. And they saved and saw the difference in the next month's chart on the shape. Another question they asked was, why is Sundays look like this and Saturdays look like this? And the answer was they rent out the building to a church group and other groups on the weekend on Sundays. So now you have a way, using this shape, if you measure these differences between the Saturday and the Sunday, you now know exactly how much you should be charging them to make sure that you cover the energy costs of them being in the building for that Sunday. So very useful tool and a way to ask intelligent questions. Finally, the question was asked, well, gee, the energy comes up very quickly. Why doesn't the energy go down just as quickly? And the answer was finally found with the janitorial department. Turns out one of the things the janitorial group did is to turn all the lights on in all the rooms and then turn them off as they cleaned each room. So they knew which rooms had been cleaned and which rooms hadn't. What that means is a lot of energy stays on through the whole night until they leave. Then there was a negotiation. How can I save and all this energy in here and get this to drop off quicker? And they made other arrangements so that they turned all the lights off and only turned it on in the room they were working in. And that made a big difference. So you can see from this chart that I've now marked up, you can A, ask a lot of intelligent questions. B, once you understand the answers, you can either charge accordingly in the case of renting the building, or you can purchase additional software to change the characteristics, or you can change the operations of how the building is used in the case of the janitorial service and save energy. So I highly recommend that not only you get used to the math and the volts and amps and watts, but find a way to chart your information and make it extremely useful for managing energy costs. So now that you have all these formulas and maybe even ways to graph it, this is my recommendation for ways to think about, I'm going to make a change. There are behavior change you can make. Don't waste energy, as simple as turning off that light switch when you leave or putting in motion sensors. Changing the behavior can change how costs work. Don't waste energy. deferred maintenance, we talked about the efficiency rating. If you don't do maintenance on the equipment, the motors, the refrigerators, air conditioners, any of the equipment, that efficiency rating will start to go down, and you can actually calculate how much is it costing you to have the efficiency rating go from one level down to another. That makes the deferred maintenance, that makes maintenance look a lot more worthwhile. Process. Improve the operating procedures and processes to gain efficiency and reduce costs. Measure and monitor energy and operations to detect unexpected conditions. We just saw an example where the janitorial staff, we changed their process, and that changed a dramatic impact on the bills. Finally, the equipment. Replace the old equipment with high efficiency equipment with long lives. This gets to that purchasing decision, whether you're putting labels on it to make sure that in an emergency it gets replaced with the efficiency, or make sure your purchasing manual and purchasing decisions are based on efficiency ratings of the new equipment, not just what's the cheapest motor or the cheapest refrigerator. So this is the three ways I look at making decisions and taking initiatives. So what are your next steps? You've been to this Calculating Energy Costs webinar. I would start with this. Establish and manage feedback process to measure and monitor the energy use from operations. You saw how quickly you could ask intelligent questions by monitoring. Just do nothing but monitoring, measuring against your own one period against the other. What does 1 week look like the next week? 1 year look like the next year? See the differences and ask questions. Another way you can do it is compare energy use with a benchmark, industry standards, or baseline. Again, your own information. You may find that if you have an office building, there are standards of how many kilowatt hours per square feet might be the standard for an office building, or food processors. There are lots of industries that have standards of energy per pound. So ask one of the energy experts in the contacts you'll see at the end, the next slide, and they may be able to provide you with that. Develop and maintain a list of project ideas. We talked about going to a budget manager, and the payback period may not be good enough right now. And so no means, gee, my project was disapproved. I would recommend that you keep that project alive, and every 6 months or so check in. Maybe the price of equipment changes. Maybe the rebates now are suddenly higher. The cost of electricity has changed. There are lots of things that can change that formula from no to yes. So no doesn't mean never is what I would say this stands for. Keep that list alive and keep checking it. Finally, stay abreast of changing technology, the energy prices and incentives. Efficiencies also change. Every 5 years or so, the efficiency quite often jumps with particular kinds of equipment. It's constantly changing. Watch for changes in efficiency. Finally, I'd say once you're on the right track and you have some questions like the variable frequency drives or how does the efficiency change with different loads, those kinds of technical questions, you would definitely want to get a hold of a full engineer that can get into answering those questions for you and analyzing your operations. You can go to or contact Paula Conway. Here's her phone number. Here's an email box that she can monitor. And there are dozens of energy experts in lighting and motors and all kinds of equipment in commercial and industrial operations that can be brought to bear on your operation, on your business. So with that, we've covered a lot of ground, and I'll turn it back to Beth.
Thank you, John. Before we move on to the question and answer portion of the webinar, I'd like to remind you that you can continue to submit questions to me through chat. Just keep them coming and I'll fit them in there as we go through our list. And let's see, John, looks like our first question is, one moment, let me get myself organized here. Where do I find the amount of watts used for a specific piece of equipment? And where can I find yes, sorry, that's a separate question. Where do I find the amount of watts used for a specific piece of equipment?
As I mentioned earlier, you can find it on the box when it was purchased. If you don't have that, you can look for a nameplate that is on the equipment. For light bulbs, it's often printed in very tiny print right around the rim somewhere. You may have to look for it. And finally, if you don't have either of those, you need to ask an expert in that equipment. It could be taking it to the place you purchase your lighting or equipment, and they will see it and go, oh, I know that, that's a model, whatever, and tell you. Or it could be that you need an energy engineer with a data logger, something much more complex. And again, Paula Conway would have access to people at PGE or the Energy Trust that can help you do that.
Thank you, John. Our next question, which I think is kind of a follow-on question to the earlier one, is where can I find a list of more efficient, similar equipment and the wattage used by that equipment?
That's a good question. It seems that's more like when you purchase equipment. I would go to the Energy Trust of Oregon as one place. If they're going to offer you an incentive, they're going to tell you what the specifications of the equipment have to be to get that incentive. The second thing is to look at the Energy Star website, and it has a lot of information on it, and it's a national United States Department of Energy supported website. So it's going to have very unbiased, non-sales-like information, and you can trust it pretty well. Finally, I would double-check with the Paula Conway and her contacts, because some of the energy use of equipment depends on the weather and the temperatures. So the Northwest might have a very different energy use than someone in the Southeast or down in the desert in Arizona. So climate zones can be a big difference in what you read on an internet site.
And John, would that be the seasonal energy efficiency rating?
Yes, that's a good example of something that there might be an energy efficiency rating, but seasonal means it's a very different rating in the winter versus the summer. Here in the Willamette Valley, we have 4 seasons a year, but our winter is a lot milder than the winter in Minnesota. So it's good to ask your expert in this region, which would be PGE and or the Energy Trust, then can confirm exactly whether it's going to be higher or lower than what you're reading on the label or on the internet.
Great. So Energy Star would have the energy efficiency rating, but double check with your local utility experts.
Exactly. Many of our commercial and industrial customers are going to have offices or operations in various parts of the country. They may have something in California and Oregon and Washington and Arizona. Well, those 4 states might be very different energy characteristics. And a project might be a yes in California because it has more air conditioning load, but no in Oregon because we'd have less air conditioning load. The hours of use would be very different.
That's great. That's really helpful. I think we have time for, well, we have one more question, and we do have time for it. John, you mentioned a variety of different ways of talking to purchasing managers for projects. Was there anything else you wanted to share about that? Any more information? We have a lot of people that were very interested in that topic.
In the past, we've done a seminar and I think a webinar on energy efficiency and renewables, a CFO or Chief Financial Officer look. And that's important because it put the operations manager and the financial and budget managers in the same room and developed a common language between the two. The purchasing manager and the operations manager is very similar. And if you contact Beth or talk to the Energy Trust, perhaps a future webinar or seminar could be formed and get the purchasing managers in a room and have this good discussion. For smaller businesses, the operations manager and the purchasing manager is the same person. It's a small staff and you have to be both. So in that case, this webinar gave you enough information to make the decisions.
That's great, John, and thank you. That was our last question, and I want to thank you all for joining us today.